Welcome back to another video. Let's jump right into the topic of Poisson distribution. A binomial random variable counts the number of successes in a fixed number of independent Bernoulli trials, where each trial has the same probability of success. It applies when the number of trials is known and outcomes are binary, success or failure. For example, counting the number of sixes in 10 dice rolls or the number of positive responses in a survey of 100 people are binomial processes. In contrast, a Poisson random variable counts the number of occurrences of an event in a continuous interval of time, space, or volume. The events must occur randomly, independently, and at a constant average rate of lambda. Unlike binomial random variables, Poisson does not require a fixed number of trials. Examples include counting cars crossing a bridge in an hour, customer calls received at a help desk per day, or defects in a fabric roll. While binomial models focus on a finite set of trials, Poisson is ideal for modeling rare events over indefinite, continuous intervals. Both are foundational for understanding event probabilities in statistics, with Poisson being particularly useful for processes that occur randomly, but at an average rate. In a Poisson process, the number of successes in a specified interval follows a Poisson distribution. The probability mass function gives the probability of observing exactly x successes in a given interval. It is calculated using the following formula. Take the average number of successes, raise it to the power of x, and multiply it by the constant, e raised to the negative average number of successes. Then divide the result by the factorial of x. Here, e is approximately 2.718, known as Euler's constant. The acceptable values of random variable x must be a non-negative whole number, such as 0, 1, or 2. The mean of the Poisson distribution is equal to the average number of successes, also referred to as lambda. This represents the expected number of successes in the interval. The variance of the Poisson distribution is also equal to the average number of successes, or lambda. This means that the spread or variability of the distribution is the same as the average number of successes. A key characteristic of the Poisson distribution is that the mean and the variance are the same. This makes it particularly useful for modeling random events that occur at a constant rate over time or space, such as the number of cars passing through a toll booth in an hour or the number of defects in a roll of fabric. Let's go over an example together. Assume a typical Starbucks customer averages 18 visits over a 30-day month. How many visits should the store expect, on average, in a 5-day period from a typical Starbucks customer? What is the probability that a customer visits the chain exactly 3 times in a 5-day period? What is the probability that a customer visits the chain at least 3 times in a 5-day period? Please pause the video here to take a moment and try answering these questions on your own. To calculate the expected number of visits in a 5-day period, we can scale the 30-day average rate proportionally. A typical Starbucks customer averages 18 visits in 30 days. We start by finding the daily average number of visits through dividing the total visits, 18, by the number of days, 30, which equals 0.6 visits per day. Then, we calculate the expected visits for 5 days by multiplying the daily average, 0.6, by the 5-day period, which equals 3. So, the store should expect, on average, 3 visits from a typical Starbucks customer in a 5-day period. This problem can be modeled using the Poisson distribution because it involves counting the number of events, visits, in a fixed time interval, 5 days, when the average rate of occurrences is known. Given the average rate of visits, lambda, in 5 days is 3, calculated earlier, we want the probability of exactly 3 visits. The probability mass function of a Poisson distribution gives the probability of observing exactly 3 occurrences, and it is calculated as e to the power of 3 multiplied by 3 to the power of 3 divided by 3 factorial. So, the probability that a customer visits the chain exactly 3 times in a 5-day period is 0.224. To calculate the probability of at least 3 visits, we can use the complement rule. The complement of at least 3 visits is fewer than 3 visits, meaning 0, 1, or 2 visits. Thus, we calculate the probability of fewer than 3 visits and subtract it from 1. So, the probability that a customer visits the chain at least 3 times in a 5-day period is 0.577. Here you can see how we can use Python to calculate Poisson PMFs, CDFs, and visualize them. We can use the Poisson function to model a Poisson distribution. Here as an example, I have calculated the probabilities of a customer visiting the chain exactly 3 times and at least 3 times in the Starbucks example. Thank you for your attention, and see you in the next video.